Hello everybody and welcome to Gravitational Fields lesson 6. Now in the last video we looked at gravitational potential and there you can see the definition on the screen. So gravitational potential at a point is the work done per unit mass in moving a small test mass from infinity to that point. From that we ended up with the equation V is W over M, so that comes from the definition, work done and then obviously per unit mass divided by mass, and that gave us, at least for a radial field, the equation minus G big M over R. In this video we're going to move on to have a look at a couple of the finer points to do with gravitational potential before then going on to define gravitational potential energy. First thing to have a look at with potential then is this idea of equipotentials. Now before we understand exactly what an equipotential is, let's just remind ourselves of a couple of things. Obviously we've got the equation V is equal to minus Gm over R. But one of the key things that we talked about in the last video is that potential is a scalar. In other words, the direction makes absolutely no difference whatsoever. So if I were to choose a point, say here, compared to the body that we're studying, which has obviously got a mass of big M, if I was to then have a look at where else on the diagram we would have exactly the same potential, well, I could say that at that point there, as long as the distance is the same, it will have the same potential, and there and there. And what we end up with, building up in 2 dimensions, it's going to end up as a circle, not a very concentric circle. Obviously in 3 dimensions this will end up mapping out the surface area of a sphere. Now along that line that I've just drawn, that dotted green line, everywhere on there has the same value of gravitational potential. As I said, in 2D that I've drawn there, it's a circle, but obviously when we map this up to 3D it will be the surface area of a sphere. Now because they all have the same value for gravitational potential, we therefore call this green dotted line an equipotential. Okay, and the clues in the name, really, you've got your word potential there, and obviously the word, or that prefix equi, we can see comes from the word equal. So everywhere on that line, on that dotted line, or on that surface area of a sphere in 3D, as we said, will have an equal potential. It will have the same value potential, and because it's a scalar, we don't care about direction, therefore it's always the same value. Now in a bit of a, here's one I made earlier, here now it's a slightly better than my hand-drawn equipotential diagram. So once again we know that we've got our body in the middle which will have a mass big M, and those green lines represent the equipotentials. Now to carry on with some of the ideas of trying to understand what these equipotentials are, the way that I was always taught to view equipotentials was like contours on a map, and we know, hopefully if you know how to read a map, you'll have seen contours on a map. Well, if those contours are really close together, what does that mean on a map? Well, it means that we're dealing with a steep slope. We're dealing with a hill with a large gradient. If we've got them further apart, then we're dealing with nice flat ground. The gradient of the ground is quite small. Now we can see exactly the same on this equipotential diagram here. Okay, in this area here, as we get close to the body, close to the planet, the equipotentials are closer. And what that implies then is that the gravitational field strength, little g, will be larger. When we have a look slightly further out in this area here, we can see that the equipotentials are further apart. And therefore what that would tell us is that the gravitational field strength will be lower, it will be smaller. Now if we relate that to the graph that we had in the last video of V against R, again like we said in the last video, in this sort of weird orientation in that bottom right quadrant of the graph and all that kind of stuff, but hopefully we should be able to start to get used to this by now. Well, we can see that we've got a graph, and as physicists, whenever we have a graph, obviously one of the first things that we want to do is we want to calculate the gradient of the graph. Now let's just remind ourselves how we calculate the gradient of a curve. Let's say that we want to calculate the gradient at that point there. Well, what we would do then in that case is we would get a ruler, okay, and here's the ruler, and we would use our ruler to somehow get a tangent to the curve. And that tangent will probably be around about 45 degrees, fine. That tangent to the curve will look something like that. Okay, so there is the tangent to the curve drawn in red. In order to then to work out the gradient of that graph at that point, we now just have to work out the gradient of that tangent, and that's fine, we're away. So let's do that. Well, the gradient we know is delta y by delta x, so it's delta v, that's what's on the y-axis, divided by delta r, that is what is on the x-axis. Let's then work this idea through. Now delta v, remember that the equation says minus gm over r, but we can see that when we do delta v, when we do the change in v, that value, at least when we're doing the delta y bit, the change bit, we are increasing, so that delta v will be positive, and that would be gm over r. Just so we've dropped in the minus sign to acknowledge that the change in v will be positive. Now when we divide that by delta r, sorry, I don't need an equal sign there, we are dividing by another r, and what we're left with then is that this gradient, delta v divided by delta r, is gm over r squared, because we've obviously got this r multiplied by this r on the bottom. Now gm over r squared, well, we've seen that before in the equation for gravitational field strength, but of course in gravitational field strength we've got the minus sign in there, so g is minus gm over r squared, whereas this gradient, this delta v divided by delta r, is positive gm over r squared. What we then say, combine it all together and say the gravitational field strength is the negative of delta v divided by delta r, and that is known as the potential gradient. Sticking with this study of equipotentials then, so we've just seen that gravitational field strength is the negative of the potential gradient. Now what I want to do is onto the equipotential lines, I just want to map the gravitational field lines, which we know are going to be all pointing in towards the centre of mass. Okay, just like that. Now, obviously, we describe that gravitational field pattern, that field line pattern, as a radial field. Which means that all of these field lines are simply the radii of circles. So in other words, one of them would be the radius of a circle. Now obviously the equipotentials all form concentric circles around the centre of mass. So if the equipotentials are forming circles and the field lines are forming radii, then what that means by definition is that equipotentials and field lines must therefore be perpendicular to each other. Finally then, on equipotentials, we need to relate these to work done. Now remember the definition, we know that V is W over M. Now if we were to, let's say, take a mass on this point here and we were to move it in from that equipotential to that equipotential, and let's label those as V1 and V2. Now we're obviously moving some distance there, delta R, from one potential to another. If we just have a look at that then, so delta V will therefore be, well, it's always final minus initial, we would work it out as V2 minus V1. If we take the definition then, W over M, and do a slight rearrangement, we can then see that the work done will be delta V. Okay, so I know I've thrown a delta in there, but it just shows you the change in order to do work done, multiplied by the mass when we multiply both sides by it. Now that formula is normally written as delta W. Work done change in energy is M multiplied by delta V. Now, relating that idea to the graph, and when we're dealing with gravitational potential, it is always useful just to sketch the graph out and start plotting some points on there so that we can really understand what's going on. Because, as I said, obviously in previous videos, we're dealing with this this strangely orientated graph. It's far easier just to sketch it out and then have a look at what's going on. Now, we're moving closer. Okay, so what we're doing is we're starting off with V1 being somewhere like that, and we're moving the way that we've drawn it in to another point closer to the planet, closer to the body. And what we can see there is the way that we've drawn it is that V potential will decrease. Now, if V is decreasing, what that will tell us is that delta V will be negative. And of course, if delta V is negative, going back to the equation, then work done will also be negative as well. In other words, if work done is negative, then we are getting energy out of the system rather than putting energy into the system. And that, again, if we go back to the last video, to Gravitational Fields 5, we made that argument when we came up with the definition for potential in the first place. Of course, if we go the other way round, so if we go from V2 out to V1, then at that point we are going in that direction, so V is increasing, and therefore delta V will be positive. And of course, if delta V is positive, then the work done will be positive as well, and we are doing the work. We are putting the energy into the system. Finally then, if we stay on the same potential, so let's say that we start at that point there and we finish at that point there. Okay, whether we go in a straight line or whether we go around the equipotential makes absolutely no difference. But of course, because these two, V1 and V2, are on the same equipotential, then V1 will be equal to V2, and then when we try and do some kind of change in V2 minus V1, well, of course, if those two are the same, then the change in potential is 0. When we do then delta W, so the work done is M delta V, well, because delta V is equal to 0, that also means that the work done is equal to 0 as well. So as long as you stay on the same equipotential all the way round, there is no work done. Now, when it comes to gravitational fields, when it comes to gravitational equipotentials, of course we've got the perfect, or almost the perfect example of bodies moving in circles around other bodies. We have the Earth going around the Sun, we have the Moon going around the Earth. So in the vast majority of orbits, at least remember the conversation about with eccentricity being low, we can at least get to the point where we're getting very close to assuming that it's a circle. We can see that in those orbits, overall, no work is being done in the orbit. Finally then, let's have a look at how all of this relates to gravitational potential energy. Now really, the definition of gravitational potential energy has already been hiding both in the definition for gravitational potential and in some of the equations that we've already seen. If we have a look at the definition first, we can see that gravitational potential is work done per unit mass. Now, of course, work done, we know that work done and energy, at least from a dimensional point of view, are the same thing. And therefore, if we take the definition of gravitational potential and delete the per unit mass bit, we've suddenly very easily got the definition for gravitational potential energy. On the last slide, we also said that delta W is equal to M delta V, where M, of course, is the mass of the small test mass. Therefore, if we take the equation for gravitational potential, V is equal to minus gm over r, and we multiply it by the mass of the small test mass, we get the equation for gravitational potential energy minus gmm over r. Now, of course, that equation for gravitational potential energy looks different to what you've been taught in the past, especially at GCSE. You will have been given the equation that gravitational potential energy is mg delta H. The assumption that's made to get to that equation is that the gravitational field strength is a constant. Now, what I'll be doing is an extension to this video where you can go and hopefully join me and have a look at how we can assume that gravitational field strength could be a constant under given circumstances. But in most circumstances, especially on the scales that we're looking at, we can't necessarily assume that G is a constant. Let's then insert into that equation, let's substitute in the equation for G, we know, which is minus gm over r squared. So there's the substitution that we're going to do, and we still have obviously the delta H bit. And what that then gives us is minus g big M little m over r squared multiplied by this change in height, this delta H. Now, while delta H and r, they may be different symbols, they still both mean a distance, and they both still have the unit of meters, and therefore that delta H will cancel out with one of those r's. And of course what we've done is just gone full circle back to this equation here for gravitational potential energy that we've just derived. In other words, that equation there in the red box, minus gmm over r, that will always work, whereas mg delta H, as I said earlier, we have to assume that gravitational field strength is a constant in order to make that work. And as I said, gravitational field strength can only be considered as a constant in certain circumstances. So please join me in the extension video if you want to explore where we can consider that to be the case. So here is your question for this video. Calculate the work done in moving a satellite of mass 1000 kilograms from a height of 20,000 kilometers above the surface of the Earth to a point 3,000 kilometers further away from the Earth. As usual, pause the video at this point, go away and do your calculation, and when you think you've got an answer, come back and I'll go through it. So firstly then, let's have a look. We've been asked for work done, and we know that work done is mass times the change in potential, and the mass here will be the 1,000 kilograms. So therefore what the main thing we've been asked for in this question is to calculate the change in potential, and then we can just multiply it by 1,000 and we get the work done. So let's have a think about change in potential then. Well, we know that delta V is going to be V2 minus V1. Where is going to be each one? Well, at a height of 20,000 kilometres will be V1, and then 3,000 kilometres further away, so that will be at 23,000 kilometres, then that will be V2. Now, before we start plugging numbers in, I want to do just a little bit of algebra on this, just to have a look and just make our lives a little bit easier. It's going to look messy at first, but then it will tidy itself up in a moment. So we've got the equation for potential. We know that potential, let's put it up here, is minus gm over r. So we can now start to form an equation. We have minus gm over r2. So r2 is 23,000 kilometres above the surface of the Earth, minus, and then v1 minus gm over r1. Now we do it this way because we can see that we've got a couple of minus signs here. We've got minus minus, which we know will end up as a plus. So a little bit of rearrangement and just changing the order, we end up with positive GM over R1 minus GM over R2. Now, of course, in there we've got common terms GM in both of those terms there, so we can bring those out and just say GM 1 over R1 minus 1 over R2. And suddenly we've tidied the whole thing up, and it's going to be a little bit easier just to plug these in a moment's time. Now, before that, again, as we saw in the last video, you've got the sort of classic way that we try and catch you out by saying above the surface of the Earth. Now, we know that the radius of the Earth from the data sheet is 6.37 times 10 to the 6, and really that's just 6,370 kilometres. Therefore, if you have a look at our different R's that we're trying to plug in here, well, R1 is 20,000 kilometres above the surface of the Earth. So R1 will therefore be 26,370 kilometres, and R2 is 3,000 kilometres further away and will give us 29,370 kilometres. Let's now plug this into the equation then, so I'll bring it up here. So delta V will equal gravitational constant first, so 6.67 times 10 to the minus 11 multiplied by the mass of the Earth, 5.98 times 10 to the 24. And then we're multiplying that, and I'll just have to bring this down here because I've run out of space otherwise. 1 over R1, well, R1 is 26,370 kilometres, so don't forget to multiply that by 10 to the 3. Now that's okay just to put it like that into your calculator. You don't have to worry about converting that into sort of pure standard form. Your calculator will understand 26370 times 10 to the 3, absolutely fine. And we'll obviously subtract from that 29370 times 10 to the 3. Now when we hit equals and obviously translate this value into something useful to us into standard form or SI prefixes, we have 1.55 times 10 to the 6, and obviously that will be joules per kilogram, or I would prefer to write that as 1.55 megajoules per kilogram. Now you'll notice that that is a positive value, and we'll confirm that with a sanity check in just a moment's time. Obviously the question is asking us for work done, and therefore delta W is 1,000 times delta V. So straight away it's either, depending on how you want to write it, in standard form it'd be 1.55 times 10 to the 9 joules, or of course in SI prefix style it'd be 1.55 gigajoules. As I said before then, we've always got to have a bit of a sanity check just to make sure. So we had a delta W that was a positive value because we had a delta V that was a positive value. But of course we're going from R1 to R2. Well, R1 gives us a value V1 there, and R2 gives us a value V2 there. Therefore delta V is pointing up on the graph, and therefore because it's pointing up it's moving positively on that axis. So we're absolutely right, we do expect delta V to be positive in that situation. So that's it for this video, and I know that we've crammed quite a lot into this one, but the three key things that we've looked at in this video, firstly are equipotentials, and remember that equipotentials are just lines of equal potential, equal gravitational potential in this context. We also then had a look at potential gradient, and we said that the gravitational field strength was the negative of the gradient of the potential graph. We then had a look at gravitational potential energy and said that gravitational potential energy was minus G big M over R. And now all of those were linked together with the definition of gravitational potential, which of course was V is equal to W over M. Potential was work done per unit mass, or rearranging that to say delta W is equal to M delta V. Now don't forget, I did say that there will be an extension video after this to discuss where we can assume that gravitational field strength is a constant, so I hope that you join me for that one. Otherwise I'll see you in the next video.